Hi students, this lecture is over chapter 23 on AC circuits. All right, so we have talked about AC circuits in the past, and remember what this means is that, we look at DC. DC means direct current. That means that the applied voltage, so the applied voltage could be the voltage from the battery, the applied voltage is constant in time for DC, direct current. And what this means is if, we talked about resistive circuit. So if we have a circuit with only a resistor, by Ohm's law, again, Ohm's law, I equals epsilon over R, the current will be constant as well. So the current will also be constant in time. All right. So what am I talking about? Well, I'm talking about direct current, and then we'll talk about AC. All right. So AC circuits are the topic of this chapter. Let's give ourselves some context. So if I'm talking about, and this is what we talked about in the past, and in chapter 18, is that we just had, like, for instance, a voltage source like a battery, call it epsilon, and all we have is a single resistor. All right, and so of course we know when we apply a voltage source, we get a current, and of course the same current goes across this resistor, and so epsilon's constant. So given that Ohm's law is I equals epsilon over R, epsilon is the EMF of the battery, we know that the current has got to be constant too. And so if you look at, you draw a graph in time of the voltage and the current, you might have, this might be your voltage in time, and this may very well be your current. And again, they are nothing more than just constants. So again, this is DC. Direct current, constant input voltage. That could be voltage coming out. Well, it wouldn't be voltage coming out of your wall because that's always AC. But again, the voltage that goes, maybe like a battery, voltage that applies to your circuit is a constant, and so that means that the currents are also, the current in the circuit is also a constant. Okay, we're not talking about that in this chapter though. We're talking about AC. So in our particular situation here, we're talking about, and oftentimes what you'll see a little symbol like this, arrow indicating the direction, and a little open circle at the end. And that usually means that's time varying. So we have a time varying voltage, and this is going to be a voltage that, so this input EMF, well, quite honestly, voltage, because there's a little internal resistance in the battery. The input voltage, we'll say V, is sinusoidal in time. That's a fancy word of saying it operates like a sine function. So if I were to, so typically how the nomenclature we use for AC circuits is that if it is we talk about our voltage as our current, our voltage right now in the system with a little letter, we'll say little v. So v is a function of t, and then we have an amplitude that we typically will use a capital letter for the amplitude, and then sine of omega t. So omega is the angular frequency. In radians per second. Again, the argument for a trigonometric function, like a sine function, is radians. I mean, in general, yes, sometimes we use degrees, but that's for our own convenience. The bare actual natural angular measure is the radian. And so we have omega t. So if t is in seconds, and this whole argument must be in radians, then omega has to, of course, be in radians per second. Now we have a way of going from angular frequency to regular frequency, and that is that omega is equal to 2 pi f. F is the ordinary frequency, and that's in hertz. So if you want to go to ordinary frequency, you could actually rewrite this as 2 pi ft if you wish. And that's what's coming out of your wall. Your wall has AC. Our society is wired to have a alternating AC current. So this is actually called AC circuits. AC stands for alternating current. So in the United States, I've talked about that the RMS, we'll talk about RMS again, root mean square, quantities. We've talked about this in the past as well. The RMS voltage, the standard voltage coming out of a wall in homes and businesses in the United States is 120 volts, all right? Some countries that voltage is actually 240 volts or twice, right? The standard frequency of the AC circuit is usually 60 hertz. All right, and so typically what that means is that everything flickers at about 120 times a second. All right, all your power goes back and forth over and over again. So we look at this and we say, okay, well, we have, typically, well, in the United States, frequency is about 60 hertz. So what this really means is that the voltage alternates about 120 times a second. So if you're looking at, like, let's say lights in a room, the lights will flicker 120 times per second. Now that's too fast for you to notice. Now, if you, as I said, in the past, if you, like, for instance, look at your computer screen and say, click your teeth, sometimes you'll get a stroboscopic effect. Sometimes you'll miss some frames, and then you'll notice a kind of a stroboscopic effect because you'll actually see, some of these out of place frames when you're vibrating your head, essentially by clicking your teeth. And so you know, but in general, as you're just sitting around, you know, or going about your business, you do not notice this this very fast fluctuation or flickering of the lights or flickering of everything. Your computer, or whatever, you know, whatever it is that you have this on, that's an alternating circuitry, and which is pretty much most of the electronics in your life. Now, now you might say to yourself, well, that's odd. I mean, you know, so we have to have we have a current in a wire. How do electrons get anywhere? I mean, we've talked about drift velocity in the previous lecture on chapter 20. Chapter 20, we discussed that electrons in a wire in a typical circuit travel at a drift velocity, a very slow drift velocity. Of around, we actually calculated this, about 4 times 10 to the negative 5 meters per second. So that's on the order of like 1/100th of a millimeter per second. I mean, that is very slow. So if the electrons are drifting, then, so essentially what this looks like is that if the voltage and hence the current alternates at 120 times per second, you know, the electron, and any given electron will have only traveled about 3 times 10 to the negative 7 meters before getting instructions to reverse course. Okay, and so the question really comes down to is like, well, you know, how far is that? I mean, well, that's about equivalent to 10 copper atoms. This is about the distance of 10 copper atoms. All right, that's it. I mean, so we know that we've calculated this in chapter 20. I calculated this for you. That electrons drift. I mean, it seems strange because as soon as you turn on a light, you know, light comes on. You're not waiting for it. You're not getting a delay. When you return on some sort of electronics, it comes on almost immediately. It's like, you know, it's instantaneously almost. And yet the strange thing about it is that the electrons that are actually in the conductor move extremely slowly. And so you look at this, if the current alternates 120 times per second, the electrons can only really ever go about 3 times 10 to the negative 7 meters. Then they get instructions, reverse course, and they go back, you know, and they're drifting very slowly. They're going back and forth, back and forth. And again, in any given cycle, they're traveling at most about 10 copper atoms. So you look at that and say, well, how do the electrons ever get anywhere? Right? So again, one typical perplexing question might be, how do electrons ever get anywhere? And the answer is they don't have to. Electrons don't have to get anywhere. They just have to move. The important thing is that electrons have to move. There must be a current. That is an amount of charge flowing past a point per unit time. And direction does not matter, as long as they're moving. As long as you have flowing charge, it doesn't matter if it's going to the right, to the left, to the right, to the left. As long as it's flowing past a point, that's a current. All right, so again, electrons don't have to actually get anywhere. As long as you have a flowing current, that is what matters. Now the question really comes down to is, well, again, if electrons travel so slowly, why is it that when I turn on a light switch, lights come on immediately? Why is it when I turn on my electronics, they come on immediately? And the answer really comes down to is, well, you can get charge across a point in a given time. It could be a lot of charges moving slowly or a few charges moving very fast. So again, current can be a lot of charges flowing slowly, or a few charges flowing fast. So we've calculated before, so we have already calculated that in a given conductor, there are on the order of 10 to the 28th free charges per meter cubed available. So when we're talking about moving charges, we're talking about moving a lot of charges. Now, as I said before, what really matters is the signal. So if I decide, let's have about 100 people, you know, again, pre-COVID, let's say we have 100 people and they're going to hold hands across the room. And then at the same time, I have Usain Bolt or some really fast runner who's going to start at, you know, the end of the room, right next to, say, the first person in my line. And I say, okay, I want people to just give a little squeeze with their left hand to their partner on the left, and I just want to have a signal go across the room, and I want to have, let's say, Usain Bolt running as fast as he can across there, and I guarantee you that signal will go across the room faster than any runner can go. I mean, we're talking, you know, you could think the speed of light, or you could talk about, the reaction time of a person. You'd have 100 people, a signal going across the room, 100 people way faster than you'd ever have the fastest runner run across the room in that same distance. And that's the way it is with electrons. You get the signal to reverse. That signal goes to almost all the electrons simultaneously. We say we have this signal say, okay, reverse course. Pretty much every electron in that wire gets that signal almost immediately, because it's going at the speed of light. All right, and so the order to reverse course, 120 times per second, goes to the speed of light. So all the electrons in a wire receive instructions to reverse course (120 times per second) at the same time. Because these instructions the signal travels at the speed of light, or near the speed of light. All right, so now the question still arises is, okay, I see that we can make these circuits work. It doesn't really matter, which direction current is flowing. But again, why alternating currents? Why is it that we want it? Why is it that we need to have these? And the answer is, and I've said this before too, even in the last chapter, is that you have to transform. You have to transmit, or not transmit, but you need to distribute power over power lines, over transmission lines at very high voltage in order to reduce power losses. And from there, you have to have a step down transformer to step down the high voltage from the power lines to a safe level for your house, your home, or business. And furthermore, in order for transformers to work, they rely on Faraday's law of induction. Faraday's law of induction requires it requires a changing magnetic flux. Magnetic flux must change in time for there to be an induced current, or the current in the wires of a transformer, or in the magnetic core of the transformer must also be changing in time in order to have the magnetic flux change in time. Faraday's law requires a changing magnetic flux. If the magnetic flux does not change, or the current that generates magnetic flux does not change, Faraday's law will not in any way manifest itself. Okay, so again, Faraday's law will naturally manifest if the current is constantly alternating. If you have a consistently alternating current, Faraday's law will manifest. All right, and so again, we need to distribute power over transmission lines at long distances at very high voltage. In order to minimize power losses. And we talked about that in the past. We need to use step-down transformers. To convert these very high voltages to lower safe voltages, typically 120 volts AC, in our homes and businesses. All right, transformers require changing current. Transformers require alternating current. Due to Faraday's law. That is the primary reason why we want to use alternating currents. Okay. We also alternating currents also are deal much better with rotating machinery. A lot of our machinery, whether we believe it or not, is rotating, and so that includes electrical generators, that includes motors. And so and a lot of the devices that actually make electrical generation, for instance, wind turbines or turbines being driven by water currents, those are oftentimes rotating machinery. Rotating machinery is also much easier to deal with alternating currents. I mean, again, an alternating current, we saw that when we studied both motors and generators. There is a rotating wire loop inside the motor and the generator. So again, we talk about rotating machinery, and a lot of our power is generated by rotating machinery. That also works better with alternating currents. All right, so alternating currents are more readily adaptable to rotating machinery. such as generators or motors. Compared with DC. Direct current. All right. So, and again, you know, you can almost think of our power station. You know, what it gives you in our general area, you know, whatever it gives you power in Fort Worth. You can think of those power stations oftentimes as a giant electrical generator. So a lot of your power may directly or indirectly be related to this, some sort of rotating machinery. And so again, all of this is much more easily adaptable with regards to AC than DC. All right. So again, there's many reasons why we want to study AC circuits. Okay. So now let's go back and we have now developed our three main circuit elements for any kind of circuitry in this class: the resistor, capacitor, the inductor. Let's go back and revisit each of these in the context of alternating currents. And then what we will do is, at that point, we'll put everything together. You know, we made RL circuits, we made RC circuits. Well, the next natural thing to do would be to make an RLC circuit. Put all three circuit elements on the same circuit. So again, that's what this chapter is really about. We're going to talk about each of these current elements alone on an alternating circuit. And then we're going to put them all together. And we're going to develop some new nomenclature in this chapter as well. Primarily a new problem-solving technique. All right. So what we've studied so far regarding AC circuits is just a resistive circuit. So let's go back and talk about resistive circuit. So we have the resistive circuit. All right. That circuit, so oftentimes you see a battery. We don't really draw it like, you know, this any longer. Now we draw this little circle and put a little sign, part of a sine function in there, right? That's oftentimes what we do. And again, we oftentimes have this little arrow with an open circle, and that's our alternating battery, or our alternating voltage source. And in the most simple way, we're talking about a resistive circuit. So we're just going to put a resistor on here, one single resistor, and that's it. Again, we've talked about this one before. Now, there's going to be a current I sub R going across the resistor. We'll just say current, I sub R, I guess. The current going across the resistor. Now, we know that the battery, or not the, I keep saying battery, the power source is going to be sinusoidal. What that means that at any given epsilon, there's a amplitude, EMF amplitude, epsilon naught, times the sine of omega t. Again, omega is the angular frequency in radians per second. Again, omega, angular frequency. And again, that's in radians per second. That is how fast, roughly 60 hertz usually. F is 60 hertz. Again, omega again is 2 pi f. F is typically about 60 hertz. All right. Again, omega is in radians per second. So you could write this as 2 pi ft. Now, if I use the Kirchhoff loop rule, I can state that again, watch my nomenclature here. I can state that the potential or the voltage drop across the resistor will be capital V sub R, again, sine of omega t. All right, so again, I use small letters. It's a little hard when you have letter V. I use a small letter to indicate the voltage right now. This is the instantaneous voltage. This is the amplitude. All right, so this is the instantaneous voltage. And this is the voltage amplitude. And this V sub R is particular. Again, it's across the resistor. Okay, this is the voltage across the resistor. So if when the battery EMF is at a maximum, the voltage across the resistor is at a maximum. And the battery EMF it goes through zero, the voltage across the resistor goes through zero. So again, it matches the voltage across the battery all the time. You know, throughout the process, you know, throughout the sinusoidal process of the voltage delivery from the battery, or sorry, from the power source. So again, the voltage across the resistor is in phase with the voltage from the battery, or from the power source. I keep saying battery, from the power source. All right. Now we have, you know, again, we understand that this, you know, and again, in our language in this class, we're going to use small letters to talk about a parameter that's instantaneous, and large capital letters for the amplitude. All right. And so we see that we would write that. Now I could write Ohm's law. So let's kind of write down what we know so far. We have epsilon naught sine of omega t, and so we know that the voltage across the resistor is the amplitude, the voltage amplitude, sine of omega t as well. And of course, we can use Ohm's law. And Ohm's law is going to say, well, the current, and I'm going to use little I for the instantaneous current. Well, that's going to be given as whatever the instantaneous voltage is divided by R, right? And of course, what's the instantaneous voltage? It's this. So I can also write this as the amplitude cap V sub R divided by R sine of omega t. Right, and so we see that, and of course, in general, we would say that in fact, I could actually write this as well. I could say that instead of cap V sub R over R, I could say that this is cap I sub R sine of omega t. So I can write that the current, instantaneous current, is equal to the current amplitude sine of omega t. And what is the current amplitude? Well, the current amplitude is the voltage amplitude across resistor divided by the resistance. So again, we have a relationship among the amplitudes. The current amplitude equals the voltage amplitude across, again, the current amplitude across the resistor equals the voltage amplitude across the resistor divided by the resistance. All right. Now, in general, alternating current is given by I right now, current I is magnitude sine of omega t minus phi. Phi is the phase. So what that really means is that a sine function is a sine function, right? Now, if I say, well, I'm going to start my sine function such that, that it's 0 at, say, times 0. Well, that's just the sine function is going to go up and down, periodically, and it's just going to have a value of 0 at 0. Now, I can take my same sine function and copy and paste it and say, well, I'm going to move it by some phase. So instead of saying that, I have a sine function that's going to go from positive to negative, I could say I have a sine function that looks like this, or I can say, I can just lift this up and move it down. Let's say a quarter of a cycle. Instead, I'm saying, well, how about if I start my sine function here? Well, again, it's just the same sine function. It just starts a different. It's the exact same sine function, just moved down by a phase. This particular phase here would be pi/2. Right, and so again, it's the same. It's a sine function is a sine function. The difference is, where do I move it? Where's its reference? Where do I move it? Move that reference with respect to, say, another sine function, and that's controlled by this phase factor. So, for instance, if I decide to make a phase factor 90 degrees, I'd move it down 90 degrees. It'd be the exact same sine function, just shifted down 90 degrees, or pi/2. All right. Well, if we compare the current equation and the voltage equation, we see that in both cases, the sign, they are in phase. B is 0. So for a resistive circuit, B is 0. That means that the current and the voltage are in phase. All right. So we can take a look at these two equations, combine them. So again, I'm just going to try to put all the results together here. So again, as I said, I have I sub r, which is little v sub r over r, cap R, or the amplitude v sub r over r, sine of omega t. The phase is 0. Okay, the current and voltage for a resistive circuit, AC circuit, are in phase. This means if I were to, for instance, draw a graph, here's time axis. My voltage may look like this. My current will have 0 whenever the voltage is 0, have a max whenever the voltage has a max, and have a min whenever the voltage has a min. So this is my V. So bar, again, little v, trying to. And then my current would also have a max. When this one has a max, go through 0, have a min, go through 0, have a max, so on and so forth. This would be my current. They are in phase. They have their maxes and mins and zeros at the same time. They're always in phase. Now you might say, so what? Aren't they always in phase? Well, it turns out that we're gonna see that the current and voltage are actually out of phase for both the capacitive circuit and an inductive circuit. So again, this is a special case. In this particular case, for a resistive circuit, the current and the voltage are always in phase. And again, as I said, we have a relationship among the amplitudes as well. We know that the current amplitude goes as the voltage amplitude divided by R. And this is the amplitude relation. Now, we're going to show a new problem-solving technique. And it's our new concept, and the concept is called a phasor. So again, let's take a look at particularly the look of these equations here. All right, these sinusoidal equations. I'm going to erase this picture here. Again, we're still in the resistive circuit. All right. Now, I'm going to pay attention. I'm actually going to write out the current like this. So we know that the current across the resistor is going to be a current amplitude, also sine of omega t. Now let's talk about what are called phasors. A phasor is a way of essentially looking at things that potentially are out of phase or vary with phase. Okay, so hence the term phasor. And so if we think about, if you were to go on Google and you were to type into Google, following Google search, say circular functions. You're typing the word circular function in a Google search. You would get sine, cosine, tangent. You'd say, well, wait a minute. Those are trigonometric functions. Well, turns out that these functions work off of what's called the unit circle. You learned about the unit circle if you took pre-calculus. All right, and again, the unit circle tells you that unit means 1, right? So the unit circle is essentially a circle of radius 1. And it says, you have a circle of radius 1. You can kind of think of the x and y axes. Let me draw this better. So you have a circle of radius 1. All right. This stuff of your x-axis, your y-axis, and in general, again, this is a radius 1 circle. Why it's called a unit circle. Unit means 1. We can think of this angle, let's say right here, as theta. Now, again, try to draw this a little bit better, but in general, I can have components to this circle here. So I can have, let's say I have a given radius, radial, and this radial would have a vertical and a horizontal component. So we can think of this as, let's say, my x, and this as my y. All right. Now, in general, the radial is 1. Now, if I say to myself, well, okay, I know that, let's talk about the sine function. I say sine of 0, or let's just say in general, sine function. We'll say a sine of theta. We know the sine of theta is the opposite over the hypotenuse, right? So we would say, well, okay, well, that's going to be y over the hypotenuse. Well, in this case, hypotenuse is 1. Hypotenuse is always 1. Okay, and so we would then say, okay, well, our relative y is going to be based upon the sine function. And I also know, well, I also know that, say the cosine, that would be x over 1. And if I want to figure out what r is, I'd say, well, x squared plus y squared is 1. Or I could say cosine squared theta plus sine squared theta equals 1. I mean, that's the trigonometric relationship. I mean, if you take it, the cosine of any angle, square that, add that to the square of the sine of any angle, that same angle, they'll always add up to 1. Again, that's based upon a unit circle. Well, a unit circle, as we know, goes around 2 pi. All right, and so the unit circle is set such that if I imagine the sine of 0 is defined when this theta is 0. When this theta is 0, that y value is there. Basically, there is no y value. It is 0. So we define the sine of 0 t equals 0. There is no y value when let's say the radial is entirely along the x-axis. On the other hand, we would say that, again, the y value, when you allow this spinner, this radial, to go all the way up to straight up along the y-axis, well, now everything is y. Everything is y at this point. Y is 1. So I would say, oh, well, the sine of pi over 2 is 1. Because there's no x at this point. Everything is 1. Everything is y. And then, of course, we're talking a unit circle, so that means the y is 1. I allow the spinner to keep going. Let's say it goes back to pi. Well, at that point, what? Well, now I have no y again. You go in your calculator and say, okay, well, the sine of 180 degrees or sine of pi is 0. Sine of pi is 0. Then I keep going. Now I get sine of 3 pi over 2. In this case, what? Now it's -1. It's all y again, no x, but again, y is now tilted upside down, so it's -1. So again, sine of 3 pi over 2 is -1, and then you come all the way back around to sine of 2 pi, and again, you're right back where you were at 0. So again, sine of 2 pi would be 0. Again, the sine function all depends on the value of y. Where is y? It's some value between 0 and 1. Or actually, I apologize, between -1 and 1. All right, and it just so happens that the sine function, it's based on y, because it's opposite. Let's talk about the cosine function. Cosine function says what? Well, cosine is a measure of what? It's not a measure of y, it's a measure of x. So at 0, well, the radial is along x. It means everything is x. There is no y, as I said before. Well, if everything is x, and the unit circle is the size 1, it means the cosine of 0 is 1. I allow the spinner to rotate by 90 degrees. Now I'm at pi over 2. Now I have no x. Everything is y. Well, again, cosine only cares about x. So that means the cosine of pi over 2 would be 0. I allow my spinner to keep going. Goes all the way around now. And now I come back and I'm at negative x direction. So now if I'm at 180 degrees, or pi, now everything is x but negative, right? And of course, the maximum value of x is, we're talking in a circle, so again, cosine of pi is -1. I keep going. I allow the spinner to go all the way to 3 pi over 2. And again, no x, only y. So cosine of 3 pi over 2, there's no x, it means it's 0. And finally, I allow the spinner to return back to where it was, but now it's going to be 2 pi, which is the same as 0. And of course, it's all x again, which means it's all 1. All right, so again, the trigonometric functions are defined off the unit circle. They're called circular functions. And so we use this term called phasor, which kind of takes your the argument of your sine functions. Remember, this has got to be radians. Omega t has to multiply and give you radians. Radians per second times second is going to give you radians. In general, a trigonometric argument has got to be in radians. So there's this concept of a phasor takes a look at the value that's taken on by the sine function and looks at it geometrically, looks at it graphically. And so let's see how this works. Again, so it's based on the unit circle. Now, in general, I'll have the current or the voltage, right? Let's say so my phasor, you know, I see here my voltage, the way I drew it, the voltage has, this is my cap V sub r, this is an amplitude, and this from this diagram is cap I sub r, right? So again, those are the amplitudes. Now, what I would do is the following. I would draw an axis, and this axis is going to be just like the unit circle axis. And let's say, for instance, that I have a little v sub r. Okay, and again, what we're going to see in the phasor is that the vertical is going to take on the instantaneous value of the parameter. So I'm going to draw this out in space. Now, this is going to be my voltage phasor. This is going to represent little v of r. It's going to have, oh, I'm sorry. It's going to, little v of r will be represented right here. This magnitude is cap v of r. All right, so again, the instantaneous values are projections on a vertical axis. And this phasor, the angle of this phasor spinning around, let me draw it bigger. Phasor spinning at an angular velocity omega, and this particular angular displacement of the phasor is omega t. Now, the instantaneous value is a projection on a vertical axis, and the magnitude or the amplitude is the length of this phasor called cap v of r. Trying to be deliberate here, make big letters and small letters. I just don't want to get things in the way either. So, yeah, so this is big V of r. And of course, the current is always lined up with the voltage for a resistive circuit. So I have a current. The current will start at 0. They're going to be right on top of each other. Here, I'll have an instantaneous little I sub r, and of course this magnitude is cap I sub r, and they are rotating together around at an angular frequency omega. This is the current phasor and the voltage phasor, and they're in phase, and they rotated angular at omega, and they have displacement omega t at the same time. Let's make it a point here. This is a phasor diagram. So on a phasor diagram, the instantaneous values little I sub r, for instance, and little v sub r are projections of the phasor on the vertical axis. The length of the phasor is the amplitude. Okay, so length is the amplitude. So and again, this I think when you talk about other types of circuit elements, you'll appreciate the phasor relationship. So you see in this relationship the same information is right here. So of course the epsilon is the EMF from the power supply, power source. That is going at it. That's the EMF amplitude, and it's oscillating, or it's alternating at sine of omega t. And this is the instantaneous voltage across the resistor. That is a projection on the vertical axis from this phasor. Again, this phasor is shorter than the current phasor. Both of them extend from the origin. This is a spinner. It spins around. Okay. And again, the amplitude, the length of this phasor is capital V sub r. Capital V sub r. So the capital V, the capital letters represent the amplitude, the small letters represent the instantaneous value. And it's also alternating at omega t, sine of omega t. And the current is in phase with the voltage. So the current, again, the instantaneous value is a projection along the vertical axis, and the length of this phasor, the current phasor, is the amplitude of the current amplitude. And they basically spin around at omega over and over again. They spin around at that angular frequency omega, so many radians per second, in the cadences in time t. So you can think about, instead of looking at the diagram, or instead of looking at a graph as the up and down sine function that you're used to, like you see it on the upper corner, you can actually look at it as a phasor spinning around in a circle, like a little spinner, right? That's the resistive circuit. Okay, let's now talk about the capacitive circuit. So having a resistor on it, let's have a circuit that's just going to have a capacitor. All right, so looks very similar. You're going to have this alternating power source, but this time the only thing that's on it is a single capacitor. No more resistor. Now it's just a capacitor with a capacitance C. And there's going to be some sort of a current, we'll call it little I sub C, and some potential difference, call it little v sub C, across the capacitor. And again, by Kirchhoff's voltage law, we would say, again, by the Kirchhoff voltage law, we would see that the potential across the capacitor, little v, is the magnitude cap v sub c, and again, sine of omega t, since epsilon. equals epsilon naught sine of omega t. Again, the voltage across the capacitor is going to be alternating the same way as the voltage being driven in the power supply. Okay, and again, omega is that angular frequency. Now, the question is, how do you relate? So we want to relate. We want to understand I sub c. How do you relate the current? You don't have Ohm's law anymore. What's the rule? What's the rule for current? Or what's the rule for voltage across a capacitor? Well, remember, for a capacitor, we talk about charge. So Q sub c is CV. All right, and so what's going to happen is, when I say this, it's actually going to be C little v sub c. Okay, it's the charge on the capacitor. Okay, so again, remember the capacitor deals with charge. Resistors deal with current. V equals IR for resistor. For voltage across the capacitor, it's V equals Q over C. So the natural parameter for a capacitor is the charge, not the current. All right, and so we could think of this, instead of writing little v sub c, I could write the magnitude. So I could say this, well, this is C times cap v sub c sine of omega t. I can say that too, and I can put this together. I can say, well, this is now my amplitude. All right. So, well, we want to talk about the current. What we have is the charge. How do we get from a charge to a current? Well, it's a time rate of change. Remember the current, you get to a current by talking about the time rate of change of the charge. And I'm going to need to use differential calculus. All right. So I actually have to get the instantaneous. So again, if you don't understand what I'm doing, that's okay. What's important is the result, that you understand the result of this. So in calculus, you would say, well, we want to take the limit as delta t approaches 0. We want to make these delta t's so small to be infinitesimal. Take the limit delta t approaches 0 of delta q sub c over delta t, and we get dq sub c dt. All right. So those of you who taking calculus, you would know that you'd have to take the time derivative of this. Well, time derivative, again, C and V sub C are amplitude. This is a capacitance, which doesn't change. It's a property and geometry of the capacitor. This is an amplitude. This is the voltage amplitude. The only thing that's going to change in time is the sine function. So anybody who's had calculus would know that the time rate of change of the sine of omega t, well, the derivative of a sine is a cosine. And of course, by what's called the product rule, you have to actually spit out a factor of omega by what's called the product, or sorry, the chain rule. Apologize. Chain rule. The chain rule says you pull out a factor of omega. So this becomes omega cosine of omega t. Now, if you don't understand this, it's okay. All right, and so what that means for us is that I sub c, instead of this time rate of change, I actually could write that this is equal to omega c v sub c cosine of omega t. Well, actually, let me just write this out a little bit better. So I'm going to use this relationship here. I need to take the time rate of change of this. So going upstairs, to remember this. So I'm going to say the q sub c dt c and cap v sub c are constants. So again, I'm taking a time rate of change of the sine of omega t. And again, as I said, a result from calculus is a very basic, what's called a derivative in calculus, very basic part of calculus 1. Calculus just says that this operation is equal to omega times the cosine. So this becomes my current, I sub c. This is now, I have an extra factor omega that comes out front. So omega c cap v sub c cosine of omega t. Okay, that is what the current looks like. Now, of course, what we want to actually do is we want to fix up this this current in a couple of ways. We want it to number one. Well, first of all, we want everything to kind of look like resistances. So remind ourselves. Recall that I sub r looks something like this. I sub r was V sub r over some resistance sine of omega t. Okay, and so we want to try to dress this current to look somewhat like this. We're gonna create what's called a capacitive reactance. We're gonna let what's called cap x sub c. Cap x sub c is we want to make something look like a resistance, more or less. I mean, when I say resistance, I mean resistance. Effectively, officially, it's called an impedance. All right, so what we're looking for is to develop what's called an impedance. That's what we're looking to try to make. A resistance is a form of an impedance. We're making different kinds of what are called impedances. All right, so for us to get something that looks like a V over R, I need to define a cap x of c to equal 1 over omega c. When I do that, I'll have an I sub c equaling to cap v sub c over cap x sub c cosine of omega t. For one thing. Okay. Now, I have one other way that I need to fix this up. And that is, now this cap x of c is called a capacitive reactance. It has units of ohms. As I said, when I make this capacitive reactance, I get a current that starts to look like the previous current. Now I have the I across the capacitor is going to be V. Again, this is the V magnitude. This is the amplitude V across the capacitor divided by this capacitive reactance times cosine of omega t. Okay, that's the first change I want to make to the current. But now I have the voltage amplitude divided by the capacitive reactance, which is again in ohms, is given by 1 over omega c. So 1 divided by omega c is actually in ohms. So units of ohms is the capacitive reactance. But there's still something wrong. And that is, if I make a side-by-side comparison, sure, I have the amplitudes right, but I have a cosine instead of a sine. I need to fix that up a little bit. So again, let me rewrite some stuff. So I have right now I sub C, the instantaneous current across the capacitor, is the voltage magnitude across the voltage amplitude across the capacitor divided by the capacitive reactance, cap X sub C, times the cosine of omega t. And remind ourselves that the capacitive reactance is 1 over omega c, or 1 over 2 pi f c. And the units are ohms, just like the resistance. And again, remember that omega is in general equal to 2 pi f. That's why I could write this. But I have one more job to do, and that is try to get this into a cosine or to a sine, because again, it doesn't look like it doesn't match the what the rule is, or what the current looks like going across the resistor. We're trying to make it look similar. So in general, an alternating current looks like what? In general, an alternating current is the instantaneous I is the magnitude I sine of omega t plus, or sorry, omega t minus phi. All right, now what we can do is we can take a look at what what the cosine looks like. Again, a cosine is nothing but a phase shifted sine. Okay, a cosine is the same as a sine, except it's phase shifted. So a cosine is phase shifted by 90 degrees. So one of your trig identities would be that the cosine of omega t, or a cosine of any theta particularly, would be the sine function of omega t shifted by 90 degrees. All right, so again, you take a cosine of omega t, or cosine of theta, whatever you want, is a sine of theta shifted by 90 degrees. One is the same as the other. So again, cosine omega t is sine omega t plus 90 degrees. All right, so what I can then say is that I can replace this up here. Say, okay, well, now I have sine of omega t plus 90 degrees. Now, I compare that with the general formula. So the general formula for an alternating current is I is instantaneous I is the amplitude I times the sine of omega t minus phi. I compare the two, and I can see that the phi value, the phase, is shifted by it's negative 90 degrees. So phase for a capacitive circuit, or for a pure capacitive circuit, is negative 90 degrees. Okay, and what that means is that we would say that I sub c leads V sub c by 90 degrees. All right, they are out of phase. The resistive circuit is in phase. The current is always ahead of the voltage by 90 degrees. It leads the voltage by 90 degrees. So what does that look like on a graph? All right, and so again, let's try to collect our information. I'm going to erase some of this. On a graph, it looks like the following. So again, let's draw a phasor diagram. So a phasor diagram would look like the following. So in my diagram, again, I would say, well, I have. Let's draw a couple of diagrams. First of all, let's draw an ordinary graph that you're used to. So again, the voltage is what you would expect it to be. Some sort of sine function. And this is your voltage. This is the time axis. And then your current, well, the current's always early. Okay, so what that means is that the current is going through a maximum when the voltage is at 0. The current goes through 0 when the voltage is at the maximum. And again, it's at a negative, max negative when it's going through 0. And here, and something like this. So it's going like this. Something like that. So the current, this is the current. The current is always ahead of the voltage by 90 degrees. On a phase diagram, it would look like the following. Here's a phasor. All right. Phasor would be that epsilon and V are aligned. Again, this phasor is spinning at omega t. This is epsilon and V. And again, these are magnitudes. And over here, we've got current V sub C. And the current is 90 degrees ahead. So again, I draw the instantaneous values on the vertical axis. The current is 90 degrees ahead. Again, the current leads the voltage. The current is always 90 degrees ahead of the voltage. Subtract 90 degrees and any given omega t, subtract 90 degrees. That essentially means that the current has happened 90 degrees ago. The current leads the voltage. And we have another relationship of the amplitudes. We would say that the voltage amplitude is equal to I through the capacitor, the current amplitude, times the capacitive reactance. So again, all of these relationships are going to look like V equals IR. All right. Again, R is officially, yes, we call it the resistance, but it's officially called an impedance. So the capacitance and the inductance each have the resistance, capacitive, and the inductance all have their own form of impedance. The resistor, it is the resistance itself. For the capacitor, it's called the capacitive reactance. Again, and again, as we see here, that the current is always leading the voltage for a purely capacitive circuit. Again, this has to be an alternating circuit. All right, we have one more current element, that's the inductor. This will be the inductive circuit. All right. And what's this look like? Well, again, it's going to look like what we've drawn before, the alternating power source. Okay. In this case, though, in this case, what we have on here is just an inductor. Looks like a little coil. Inductor of inductance, capital L. And again, I want to understand there's going to be a voltage the glare go away. There'll be a voltage across the inductor. Call it cap V sub L. Again, it's going to be, we'll say small v. And a current across the inductor. Little I sub L. Again, it's going to be a lot of deja vu. We know, again, that epsilon goes as epsilon naught sine of omega t. Again, the EMF varies as sinusoidally with time. Okay, and then we also know that by Kirchhoff's voltage law, we know that the voltage across because there's only one circuit element, the voltage across the inductor is going to go as an amplitude, max amplitude voltage, again, sine of omega t. It's going to be in phase with the EMF from the power supply. All right, so again, you'll have this relationship. Again, that's the same that I could write down for both the resistor and the capacitor. You always have the potential across the circuit element being in, going sinusoidally with as a sine of omega t, just like the power supply. But now the question is, well, what's the rule for voltage drop across an inductor? Well, we've had that just in the last chapter. Remember, there is the concept of Lenz's law, giving you a self-induced opposing EMF. That is what actually fights against you and causes you to have a voltage drop in the inductor. All right, and so we know that the general rule is that the voltage across an inductor is given by the inductance in henries times the time rated change of the current across the inductor with respect to, again, delta is current across the inductors with respect to t. Okay, that is the rule for determining what the voltage drop is across an inductor. Again, the rule for the capacitors Q over C, the rule for a resistor is IR, the rule for an inductor, the voltage across an inductor is the inductance times time rated change of the current through the inductor. All right. Well, again, I want to use calculus. So let me first of all, before I do that, so we know that V sub L, I can substitute in here. Well, actually, let's use calculus. So again, take using differential calculus. We know that the instantaneous time rate of change is the first time derivative. I.e., and I still want this relationship here. This space. Again, our voltage against V sub L is cat V sub L sine omega t. Just remind ourselves here. All right. We want to say that, well, we want to take the limit as delta t approaches 0 of delta I sub L with respect to t, and we would exchange our deltas for d, little d. D I sub L dt. All right. So again, what we would do is we would substitute to get the actual time rate of change. We would substitute the deltas for little d's to get the instantaneous time rate of change. Again, if you don't understand this notation, it's okay. I mean, the important thing is to understand the results of it. All right. Now, what I want, again, is the current. So let me kind of flip about the equal sign here. Say, okay, well, I have di sub L dt, and that's going to be little v sub L over capital L. Right? I just switch things around. And of course, what I can actually do is I can now substitute for what v sub L looks like. And so I can actually say that, well, this is really going to be cap v sub L over L sine of omega t. All right. Now, I don't have the current on the left-hand side. What I actually have is the time rate of change of the current. So what I have to actually do is I need to now integrate. So I sub L would actually be the integral of cap v sub L over cap L sine of omega t dt. Again, anyway, you know, if you haven't seen integral calculus, is calculus too. If you haven't seen that before, don't worry about it. The important thing is when I perform some sort of a integral like this, what I get, again, it's going to be, now, again, the integral of a sine is a negative cosine. But what I actually have to do is I actually have to divide by an extra factor of omega when I do the integration. All right. And so what I end up getting here is the following. That little I sub L, when I do this operation, I will get a negative cap v sub L over omega L cosine of omega t. That is what I get when I perform this calculus operation. And this is, again, this is integral calculus. Okay. So, and again, I need to do some fixing up. You know, that doesn't look like, I mean, again, I want to have things look like what? I want things to look like this. I sub r is a cap, I sub r, if you will, divided by, I'm sorry, it's got to be a cap v sub r over some sort of impedance sine of omega t minus phi. I mean, I need to have something looking like this. All right. And so I need to have some sort of an impedance in the bottom. I need to develop that. And then, of course, I need to change this to look like a sine function. And it's going to be the same process as before. All right. So let me write this up here. Let me erase some of the work to get there. So we now have a function, but it's not quite right yet. We need to fix it up a little bit. So I have I sub L, the instantaneous current across the inductor is negative cap V sub L over omega L cosine of omega T. Okay, so again, I want to divide the magnitude, or I want to divide the voltage amplitude by some sort of an impedance. And so I can define what is called a inductive reactance. And that's simply going to equal omega L. And again, I just need to have an impedance that's dividing, the voltage amplitude. And of course, that can be very well be 2 pi f L. And this is an ohms. Just like resistance, just like capacitive reactance, this is called the inductive reactance. Okay, it's a way of fixing up the current to look like, kind of a uniform, if you will. I want it to look like the resistor. Okay, so we want to make it look like, that there is a voltage amplitude divided by an impedance times the sine function with the right phase. All right, so we got one of our things answered, and I can now actually write that I sub L. I can actually write that this is going to be cap X sub L, provided again that X sub L is this, based on the conductive reactance. I got part of it done. The other part, though, is I have this negative cosine of omega t. Well, we go back to our trig identities. Again, it's another phase shifted sign. Turns out the negative cosine of omega t, I can actually write that as the sine of omega t minus 90 degrees. Last time it was plus 90 degrees. This time it's minus 90 degrees. And I want to compare with the general formula for an alternating current. And that is that the instantaneous value of the current, little I, is the current amplitude sine of omega t minus b. So comparing the two, we clearly see that now B is positive 90 degrees. And we say that the current lags the voltage. So I sub L lags V sub L by 90 degrees. Right? So the current is behind the voltage now by 90 degrees for the inductor. The capacitive current leads. The capacitive current leads the voltage by 90 degrees. The inductive current lags the voltage by 90 degrees. Right? And so what does this look like? Well, if I were to draw, again, my ordinary curve, I have my sinusoidal curve. Here's my time. Let's see, here's my voltage again. Again, this is my V across the inductor. Well, now the current is always late. And so we actually see it going down here. so on and so forth, right? I mean, it's hard to draw this. But it's late. This is your I sub L. It lags by 90 degrees. How would you draw this on a phasor diagram, which would be a little easier to see? Well, if this is my voltage, cap V sub L, let's say that corresponds over to a little v sub L. Well, again, the current is behind, it lags. My current would be going down like this. All right. So again, by what? 90 degrees. The current lags. It's behind the voltage by 90 degrees. All right. So let's kind of summarize what we said. Oh, and by the way, we also have another relationship among the amplitudes. Again, the voltage amplitude is the current amplitude across the inductor. Again, times the inductive reactance. Let's put all this together. Summarize it. So again, we made alternating currents for each and every one of our three circuit elements: the resistor, the capacitor, and the inductor. So there's a nice table here. Phase and amplitude relations for alternating currents and voltages. All right. And this is just a little table that summarizes everything. So let's make a little table here. We have circuit element. On this column, we have their symbol, the impedance, phase of the current, phase angle, phi, and the amplitude relation. You know, all the stuff I have said, but let's put it all together. All right. So the three circuit elements that we can talk about are the resistor, the capacitor, and the inductor. We made circuits for each of these all by themselves, right? Now, the symbol for the resistor, of course, is R. The symbol for the capacitance is capital C. For the inductor is capital L. Okay, what do we call the impedance? Well, the impedance for the resistor is the resistance itself, R. For the capacitor, it is the capacitive reactance, cap X sub C. For the inductor, it is the inductive reactance, cap X sub L. What's the phase? Well, the phase again, this is the phase of the current. Well, the current is in phase of V sub R. For the resistor, for the capacitor, it leads B sub R by 90 degrees. And for the inductor, it lags B sub R by 90 degrees. Okay, just like I said, the phase angle, your angle phi, phase angle for the resistive circuit is 0. They're in phase. The phase angle for, since the current is early, the phase angle is negative 90 degrees. For the capacitor, the current's late, it's lagged, so it's positive 90 degrees. You have to add 90 degrees to everything to make up for the current, because the current lags. And the amplitude relation, well, here we have, again, these are amplitudes. B sub R is cap I times R. And it's always the voltage amplitude times equals the current times the impedance. Here is the B sub C is I cap X sub C. And B sub L is I cap X sub L. We're trying to make everything look like Ohm's law as best we can, and try to make everything uniform so we can compare apples and oranges. Now, there's a cute way of remembering this lead lag relationship, and it's always remember Eli the Iceman. So typically, sometimes we use, instead of V, we use E or epsilons for the voltage. So we're kind of using, instead of the voltage, we're thinking that we generally are using it as E, like epsilon. And so you look at this and say, okay, Eli, E-L-I, what does that mean? That means that for the inductor, you see that the voltage is ahead of the inductor, right? Well, for the inductor, the current lags the inductor. So Eli, E-L-I, if you look at it, here's the inductor, and the voltage, their current is coming after the voltage. ICE, I-C-E. Here you see the current I is ahead of the voltage. The current leads the voltage for what? The capacitor. In Eli, the L stands for the inductor. The current is behind the voltage. It lags the voltage. Whereas for ICE, I-C-E, here's C for the capacitance. I is coming before E. Current leads the voltage, right? So Eli the Iceman. The way, oftentimes a way of remembering the lead lag relationship. Okay. All right, let's do a few problems. And some of these concepts, some of you guys have never heard of these before in your entire life. So again, let's kind of get some concrete to it. All right, let's look at open stacks. Now again, interestingly enough, we are on chapter 23 in Cutnell and Johnson now, and in fact, we're still on chapter 23 in open stacks. And what we called chapter 22 and 23 for us is all 23 in open stacks. So we're kind of at the tail end of open stacks. Chapter 23 in open stacks basically took forever. So we're now we're still in chapter 23 of open stacks, right? So open stacks 23.79. All right, that says is at what frequency will a 30.0 millihenry inductor a reactance of 100 ohms. Now, there's one thing I didn't really point out so much, and that is there's something kind of funny about these kinds of impedances compared to the resistor, is that unlike the resistor, the capacitive reactance and the inductive reactance actually depend on the frequency of the alternating current. The resistor does not. So if you take a look at the inductive reactance, you know, cap X of L is omega L, or 2 pi f L. So given the frequency of the alternating circuit, you know, the inductive reactance changes with respect to that. So the inductive reactance is actually more dominant at high frequencies than at low frequencies, right? So, you know, it's directly proportional to the frequency. Whereas the capacitor reactance, 1 over omega L, or omega C, sorry about that, which is 1 over 2 pi FC. So for low frequencies, the capacitive reactance is dominant. And at high frequencies, it becomes small. So again, high frequencies, the inductive reactance is dominant. At low frequencies, it's small. Whereas it's the exact opposite. At low frequencies, you get your numerator, your denominator gets smaller and smaller. The capacitive reactance is dominant, and it gets small at high frequencies. So these dominate at different parts, at different levels of frequency. All right, so there is a frequency dependence, and we're going to kind of see that very strongly when we put everything together and make an RLC circuit. So that's the funny thing to keep in mind here, is where the impedance for a resistor doesn't matter. It has no frequency dependence at all. All right, so so in this particular case, we're saying, well, we have an inductor on this little inductive circuit of 30.0 times 10⁻³ henries. And we also have we're told the inductive reactance is 100 ohms, and we want to find what the frequency is. We can just solve this equation for frequency, and so we get F is cap X of L divided by 2 pi L, and I'm just solving for the frequency, or 100 ohms divided by 2 pi divided by 30.0 times 10⁻³ Henry. If I do all of that, I get 530.5 hertz. So requires to have 100 ohm inductive reactance, requires for this particular inductor requires a frequency, AC frequency of 530.5 hertz. Okay. Next problem. OpenStax 23.81. All right, that says what capacitance should be used to produce a 2.00 mega ohm reactance at 60.0 hertz. Typical frequency coming out of your wall. All right. Well, what are we told? Well, we're told the capacitive reactance. That's what we want. So CapX sub C is 2.00 mega ohms, or we want to have everything in base SI, so 2.00 10 to the 6 ohms. The frequency is 60 hertz. As I said, the capacitive reactance is 1 over omega C. But omega is 2 pi f, right? So it's going to be 1 over 2 pi f c. So I want the capacitor. I want the capacitance. So I solve for the capacitance. I basically changed partners here. So C is 1 over 2 pi f CapX sub C. Or 1 over 2 pi, also in the number 60 hertz, and CapX of C we're told is 2.00 times 10 to the 6th ohms. When I do this calculation, I find out that the capacitance necessary, I need a capacitor, the capacitance of 1.33 times 10 to the negative 9 farads. Or another way of saying this is C equals 1.33 nanofarads. All right. All right, here's another one that kind of, this problem, I like this problem in that it kind of tells you what effect frequency has on these various items. So let's look at 23.83 of OpenStax. All right, look at that. All right, 23.83. Next problem. All right, OpenStax. 23.83. Find the current through a 0.500 Henry inductor connected to a 60.0 hertz um, 480 volt AC source. So probably not in the United States, probably somewhere in Europe. And then that's part A, I guess. Part B, what would the current be at 100 kilohertz? All right, so we're going to consider the same inductor. The inductor again has inductance of 0.500 henries, but we're going to connect it across a 480 volt AC source at 60 hertz. Then we're going to see what would happen to the current at 100 kilohertz. All right, that's where we're going with this. All right, so I need some real estate here. So, all right. Okay, the inductance for this inductor is 0.500 Henry. The frequency right now is 60 hertz, which is typically what comes out of your wall. Epsilon, the voltage, is going to be 480 volts, and we can refer to that as our cap V sub L. Again, that's, there's only an inductor on this, so whatever's coming out of the wall, that's going to be the voltage amplitude across the lone inductor as well. We can use the amplitude relations to find the current. So using the amplitude relation, again, everything has to look like Ohm's law. So cap V sub L is I cap X sub L. We can solve for I. I is cap V sub L over cap X sub L. All right. Now, we need to find out what cap X sub L is. Okay, so cap X sub L, we're talking about an inductor. So again, what's the formula for inductor? It's omega L, or otherwise known as 2 pi f L. So cap X sub L is 2 pi 60 hertz times 0.500 henries. Cap X sub L, the capacitive reactance, the inductive reactance when I do this, 188.5 ohms. Now, simply it's to put everything together. My I now is simply going to be cap V sub L over cap X sub L, or the 480 volts divided by 188.5 ohms. The current through the inductor at this point will be 2.55 amps, 2.55 amperes. Again, I needed to know, so I was given the inductance, I was given the amplitude of the from the voltage source, and of course that's the same as the amplitude of the voltage going through the inductors. Is all I have is one inductor on the circuit. And this again, it would be via Kirchhoff's voltage law. And I know the frequency is 60 hertz. I can use the relationship of the amplitudes. The voltage amplitude across the inductor is a current times the inductive times the inductive reactance. I can use that to find the current. The thing I don't know yet is the inductive reactance. The inductive reactance is omega L or 2 pi FL. Well, I know all that, so I can get the inductive reactance of 188.5 ohms. And then I can plug into the formula, 480 volts divided by 188.5 ohms. I get 2.55 amperes. Now, let's pay very careful attention now. Very close attention. Because I kind of want to make a comparison here. So I'm going to parking lot some of these answers so that when I do part B, we can kind of compare what's going on. All right. And so let's put the answer in the parking lot. The current, again, for part A, again, keeping in mind, frequency is 60 hertz. And I get a current of 2.55 amperes. Again, now, what happens if I go to part B? Well, all the work is the same, except I have a larger frequency. Part B, my frequency is 100 kilohertz. same inductor. What changes now? Well, again, I use the exact same relationship. I know what V sub L is. I now have to calculate CapEx sub L. Again, it's the same formula, except this is 100 kilohertz. Again, my inductor is the same as 0.500 henries. And I do that calculation, I will then get a much larger value for inductive reactance. I get 3.14 times 10 to the 5th ohms. Okay, I put that capacitor inductive reactance into the final formula for the current, and then we'll see what happens. 3.14 times 10 to the 5th ohms, and I find out that the current has gone way down. Current will be 1.53 times 10 to the negative 3 amperes, or 1.553 milliamperes. Okay, so we see that the inductive reactance dominates at high frequency. So again, that is like an impedance. The current, you can see, has gone way down because the inductive reactance has gone way up. Okay, that's the inductor's equivalent, or that's the inductor's analog, if you will, to resistance. That's its impedance, called the inductive reactance. It depends on frequency. At a lower frequency, you know, I had a much smaller reactance. My inductive reactance is only 188.5 ohms, and I got a current through of 2.55 amperes. I increased the frequency a lot. I mean, I increased it to 100 kilohertz, and now my inductive reactance has gone way up, 3.14 times 10 to the 5th ohms, and then that's taken my current way down to 1.53 milliamperes. So again, the frequency of the alternating frequency of the alternating voltage source plays a huge role in the determination of the reactances. Okay, now okay, let's go to the next topic, and really pretty much the last topic, and that is the next natural thing we want to do. We've talked about we now have all three circuit elements: the resistor, the capacitor, and the inductor. We have now employed them individually in AC circuits. Okay, so now, and we've developed our concept of the phasors. Now what's left, the most natural thing, and also, by the way, we've also done RL circuits and RC circuits. The most natural thing of all would then be to put everything together. And that would be called the RLC series AC circuit. Putting it all together. So what does such a circuit look like? Well, again, it will be on an AC power source. Okay. And essentially it's going to be, as RLC says, resistor, inductor, capacitor. We're going to put all three of those together. All right, and so draw it out. Let's see, I have a resistor, capacitor, and an inductor. All right, so this is the full souped up circuit. about the last kind of circuit we're going to do in this class. All right. So the resistor has a resistance R, the capacitor has capacitance C, the inductor has inductance L. And there is really one common current that goes through this circuit. I've been kind of careful talking about I sub C and I sub R and so on and so forth. But when you put everything together, they are in series. What that means is they're along a common circuit path. They all have the same current going through them. All right. So at this point, you might think, oh, well, he did a differential equation to solve for the RC circuit. He did a differential equation to solve for the RL circuit. He's probably going to do a differential equation to solve for this. But in reality, no, we're going to do an alternate method. This will be the same method that's used in university physics as well. We're going to use our phasors. All right. And so we're going to use this via a phasor diagram. So first and foremost, in looking at this, let's kind of start off with a phasor diagram. Okay. Now, I'm going to draw a current, magnitude I. Again, this is going to go up by some omega t minus phi in the most general sense. Again, there's only one current in this circuit. All right, there's only one current, so I literally have just one current. I don't have a current for each type of circuit element. There's just one common current. There's the current part of the phasor. Now, we use Kirchhoff's voltage law, like we would if we were doing differential equations. So using the Kirchhoff voltage law, we may write epsilon. We can write a relationship among the instantaneous variables. So epsilon is going to equal little b sub r plus little b sub c plus little b sub l. Again, these are the instantaneous variables. All right. Now, if we put these on the phasor diagram, what are they going to look like? Well, the resistor will be right along the same direction or along the same phasor as the current, right? Because it's in phase with the current. So the resistance would go like this. This would be cap V sub R. And this would be the instantaneous V sub R. Again, it is in phase with the current. The resistance is in phase with the current. Now, what did I say? So again, Eli the Iceman. So so we have that let's see here, Eli the Iceman. Remind ourselves. So again, the voltage, the epsilon will be going, going along this with this current or well, the current. So essentially, what happens here? So the current leads the capacitance. All right. So the current is ahead of the capacitance, ICE. The current leads the voltage. All right. So that means the current for the capacitor happens before. Give me 1 second here. Right. So yeah. We would have the B sub L out here, like in the previous diagrams. And that's a 90-degree angle. And on the other side, be B sub C. And that's also at a 90-degree angle, right? According to Eli the Iceman. Now, what we could do is, we know that, let's see, let me try to draw this in a nicer way. Let me try this. Okay, so let's say I draw it this long. This would be little b sub L. This would be little b sub C. Again, instantaneous values. They relate to epsilon in this particular manner. They add in this way. They algebraically add. The instantaneous values do. Okay. Now, let's fix this up a little bit. So again, we know what we're doing. So let me, I'm going to redraw this over here and make it bigger. So again, we have an RLC circuit. We need as much space as possible. So again, I'm going to, again, originally, so let's redraw this diagram. The diagram really is everything for us. So we need to draw it well. And we're doing this whole solution with phasors. Here's the current. It's going up by omega t minus phi. All right, so current leads the voltage for the capacitor. Eli the Iceman. And the current lags the voltage for the inductor. We'll say that this is cat V sub R. All right. Now, one of the things we can do is we notice that cat B sub L, the B sub L and B sub C, the phasor for the inductive voltage or voltage across the inductor and the phasor for the voltage across the capacitor are anti-aligned. I can actually subtract one from the other. So I can actually do is I can actually subtract them and write it this way. Right, is as a difference. And it'll be a different length, but this would then become, again, be let's say a different length, a shorter length, whatever you want to call it. A new length. This would now become cat B sub L minus cat B sub C. It's now the difference. All right. Now, all right. So right now we have the current phasor, the phasor for the voltage across the resistive phasor. They're always aligned. And then again, this is a 90-degree angle. And here is this represents the inductive voltage minus the capacitive voltage. Okay, so that's what this is. Again, this is a phasor diagram. Now, it's going to be, and again, we also know that epsilon is, these are the instantaneous variables, V sub R plus V sub C plus V sub L. We know this, again, from Kirchhoff voltage rule, or voltage law. This is the relationship of the instantaneous variables, basically the values along the vertical axis. Again, we got this from the Kirchhoff voltage law. Now, there's a funny thing that, again, you have to kind of read this a few times, you see this, but in vector operations, okay, the algebraic sum of the projections on a set of vectors okay, on a given axis, so in this case, the vertical axis, is equal to the projection of that axis of the vector. Okay, and the vector sum, I should say, of these vectors. Now, what does that mean? Well, that means that I can actually imagine if I add up all these vectors, you know, I get epsilon. Well, I can write epsilon as yet another vector in this space that it also projects on that axis. And so if I write this very carefully, and again, I got to do this very carefully here. I can write another vector epsilon. So I'm going to kind of make a guess. Epsilon's going to look like this. My epsilon vector. Now, my epsilon vector, if I draw this carefully, let's see. My drawing skills that are better. You can see this better. All right, so let's project vertically. I drew this too long. All right. Let's imagine for a moment that I didn't draw this resistor all the way out here. I actually drew it here instead. All right, there you go. So we'll say that this is V sub R. Okay, so I will draw an epsilon. I'm gonna make this guy a little bit longer. Again, this is my drawing skills. I apologize. All right. So what I wanted to do, give it a little bit longer. All right. Epsilon. All right. This is my V sub L minus V sub C. Okay, this is a 90-degree angle, and this is a 90-degree angle from V sub R. All right. So this length of this vector is also v sub r. And this length is cap v sub l minus cap v sub c, and this is a right triangle, which means I can actually use the Pythagorean theorem to essentially essentially compare or write a relationship that utilizes all the amplitudes that I have of all the various vectors involved. All right, so you can kind of look at this, and you can kind of look and see, okay, well, what do I have now? Well, I have omega t minus phi to get here, and this is going to be 90 degrees. So actually, the angle between the current, this angle here, is actually going to be phi. The angle between the phase angle between the actual epsilon, again, the phase angle epsilon should actually go along with, there should not be any kind of phase difference here. Now, if phi was 0, they're lined up, right? But in general, epsilon is going to have some sort of there's going to be a certain omega, a certain angular frequency that is going to be associated with the power source. The current may or may not be lined up with that. If the overall current in the circuit has any kind of a phase shift, it's going to be phase shifted from epsilon. Because in general, the current looks like this. Remember, the current in general looks like cap I sine of omega t minus phi. So we allow the current in general to have a phase angle phi. That means that there will be a phase angle between the epsilon just got done drawing, which is basically from the fact that Kirchhoff's loop rule says that I have all of these projections along the vertical axis have to have this relationship, and combined with the fact that there also has to be a phase difference that I must build into this picture to allow the current to be different than the actual EMF. All right. So if I do this, I can now use Pythagorean theorem. So I can now relate all the amplitudes via Pythagorean theorem. So we can relate the amplitudes. This is actually epsilon naught. The amplitudes, epsilon naught, IR, or actually cap V sub R, cap V sub C, and cap V sub L by the Pythagorean theorem. And what would that be? Well, again, I'm looking at this particular triangle. Maybe I'll put it in red. This little triangle in red. I'm looking at that triangle. So again, let's just write out what the relationship is. Let me kind of go over what I said here. So the Pythagorean theorem would say that epsilon's not squared, and the amplitude from the sinusoidal EMF in your power source is going to be what? It's going to be this leg squared plus this leg squared, right? So it's cap V sub R squared plus the quantity cap V sub L minus cap V sub C squared. Okay. So again, that is what the Pythagorean theorem tells us, or if we want to be more exact about it, we'd say, well, cap epsilon naught squared will be IR quantity squared plus, well, what do we have here? It's going to be the square of I cap X sub L minus I cap x sub c. So I can actually pull a square I squared out of everywhere. I can factor out an I, that becomes an I squared, and I can pull an I squared out here. So I can actually write that epsilon naught squared is I squared times what? R squared plus the quantity cap x sub L minus cap x sub C squared. Or I can write that epsilon naught is equal to the square root, or sorry, it's equal to I. And actually I can do it up here. Well, yeah, let's do this. Epsilon naught, again, taking the square root, you just get I, not I squared. And then you have what? You have R squared plus cap x sub L minus cap x sub C squared, and that's all to the 1/2 power. All right, that's 1/2 power is the square root. So altogether, we can solve for I as a function of R. And I can write this as simply I. So divide the square root underneath, and I can write this. I can say that I is epsilon naught, the maximum EMF from the power source, divided by the square root of R squared plus cap x sub L minus cap x sub C quantity squared in the square root. All right, and we call this Z for impedance. So altogether, we can write that I is epsilon naught over Z, and Z is R squared plus cap x sub L minus cap x sub C squared. Z is called the impedance. It is an ohm. All right, so let's repeat what I did. I did a lot of geometrical arguments here. Okay, so I drew one I phase, one current phasor. There's only one current in all of the RLC circuit. Okay, I know that Eli the Iceman okay, the resistor I know is going to go always in phase with the current. I know the current leads the inductor. That means that the voltage leads the inductor. So for the inductive voltage, it's going to always lead the current. So for the inductor, Eli, the voltage. So remember the EMF, if you will, we use E instead of V. In old nomenclature. So again, this is like the voltage leading the current for the inductor. Voltage leads the current for the inductor. So again, the voltage comes 90 degrees in front of the current. So the voltage is going to be 90 degrees in front of the current. ICE, the current so the current, so the voltage lags the current. So again, the voltage is going to be behind the current, 90 degrees. So again, I should have, so again, voltage leads the current for the inductor. So that means the voltage is ahead. The voltage should be, voltage across the inductor should be 90 degrees ahead of the current. ICE, that means the voltage lags the current for the capacitor. So the voltage is going to be lagging by 90 degrees. Why did a subtraction? I made one vector, V sub L minus V sub I. Okay, and then I know by the Kirchhoff loop rule that the instantaneous, the projections of epsilon And the EMF, again, if the EMF is going around in a phasor as well, its projection on the vertical axis is equal to the sum of the projection of the resistive voltage on the vertical axis plus the projection of the capacitive voltage on the vertical axis plus projection of the inductive voltage. Again, a projection is a fancy way of saying, if I were to draw, a component, what projection, what component does that vector have on that axis? I can say component, or I can use the word projection. Both are equivalent. So I have a relationship among the projections of all these vectors on the vertical axis. And in fact, I can utilize that information and say that I have a vector sum that represents epsilon naught. And I happen to know that it's got to be, if this is omega naught minus phi, which is a generalized relationship for a current with a phase factor, well, then that means that we always know that the power source, the epsilon, has a frequency omega. So it's going to have a phase angle difference with the current of phi. So I know where to place the epsilon. And by the way, these amplitudes essentially form a right triangle with this. So again, the way you draw this in, cap V sub r. This is the voltage amplitude. They're capital letters. And cap V sub L minus cap V sub C. This is a right triangle. I can now use Pythagorean's theorem to relate all the amplitudes. That's all I did. And then I just said, well, what is cap V sub r? Well, that's IR. So again, I know the amplitude relationships, right? That's I cap X sub L, inductive reactance. Minus, that's cap I times cap X sub C. That's the capacitive reactance. I'm able to pull the current out of this bracket. Well, that becomes I squared because this bracket is squared. And I pull the current out here, that also becomes I squared. So I pull out I squared. What I'm left with is R squared plus, again, this difference, cap X sub L minus cap X sub C squared. And then I take the square root of both sides. This becomes epsilon naught. This becomes I. This becomes the bracket to the 1/2 power. And then I can just do what? I can solve for the current by just dividing both sides by this square root. I have I as epsilon naught divided by the square root of R squared plus cap X sub L minus cap X sub C quantity squared. And what you see here in the square root is the official impedance. I can actually write an overall Ohm's law, if you will, for the RLC circuit. And instead of having like an R down here like I would for a basic DC inductive circuit, now I have a Z. The Z is the impedance. So again, I've generalized this relationship for an overall RLC circuit. All right, and so now I can go one step further, and this is the result I'm after. Okay, so I go one step further, and I'm going to erase this picture here. The result that I want for the RLC circuit again is that the current in this is the current amplitude in the RLC circuit. The current amplitude. These are amplitudes, mind you. The current amplitude is the amplitude of the voltage source, the EMF, divided by the impedance. And the impedance is the square root of R squared plus parentheses cap X sub L minus cap X sub C. And then to be more explicit, Z equals, we have square root of R squared. What is cap X sub L? It's omega L, or 2 pi F L. What is cap X sub C? It is 1 over 2 pi F C squared. That is the impedance in its most glorious form. So remind you, this is a current, this is the impedance. All right, this is an impedance for the RLC circuit. The units, ohms, given by the symbol, just like the resistance. All right, and so this is the most generalized impedance. This is current amplitude. This is a relationship among the amplitudes. All of these are amplitudes. They're not the instantaneous value for the current. Now, so let's write this out in the all glorious form, and I want to see something else here. So I'm going to actually write the current amplitude, and then let's take a look in general here what it looks like, and then we're going to see something that's even more interesting. All right. So all together, I can write I'll just write this. I is epsilon naught divided by the square root of r squared plus, again, parentheses squared of 2 pi fl minus 1 over 2 pi fc. Okay, again, current amplitude. Now, and you can also see this in the following way. You say that I is equal to epsilon naught divided by r squared plus parentheses omega L plus 1 over omega C. You look at it this way as well. Okay, that's another way of looking at it. And I'm sorry, this is a minus. Now, so we have a rational expression. And of course, anytime you talk about a rational expression, you want to ask yourself, the question is there some way I can get in trouble here? Is there something that can go wrong with this function? Or what is the smallest value this function could take on? All right, and so if you look at this, I'm going to particularly look at this formula here for the current amplitude. This is a more generalized one, but let's look at this one. So at what value of omega, or at what condition, is Z, the impedance, a minimum? And I, the amplitude, the current amplitude, a maximum? Well, that condition would be, there's nothing I could do with this term here. R squared is what it is. But I can make this a minimum if I make this particular square go to 0, i.e., if omega L minus 1 over omega C is 0. If this parentheses is 0, then I have the largest current amplitude that I could possibly have. If that's the case, then I becomes epsilon naught over R. Literally, any kind of effect from the inductor or capacitor will cancel each other out. In this particular situation, if this parentheses is 0 and this becomes square root of R squared, just R. And this occurs how? Well, this occurs if omega L equals 1 over omega C, or omega squared equals 1 over LC, or omega, and I'll call this omega naught, equals 1 over the square root of LC. This is called a resonance. It's the same kind of resonance that you studied when we talked about the full-blown forced harmonic oscillator. We talked about, I showed you the Coleman-Narrows bridge falling, basically being shaken apart by winds. Essentially, omega became very close to omega naught, and you had a resonance. This is the same kind of thing. This is a resonance in your circuit. So your current amplitude reaches a maximum when omega, or we call this omega naught, or omega is equal to 1 over the square root of LC. We call that omega naught oftentimes. So omega is taking on that value, and that is the resonance value. Okay, so we have such a thing called a resonance. Very important, particularly when you're making radios, trying to tune a radio. Again, resonant frequencies are very important. I mean, you get a nice sharp resonant frequency, you can get a radio station. Okay, going back to that diagram, which I erased. Remind ourselves here for a moment that I had a right triangle. Let's see if I can try to draw at least the part that matters. Okay, I'll do some problems to kind of clear these concepts up. But let's imagine, remind ourselves here that we had a right triangle. In this right triangle, I drew an epsilon naught. And then I had, let's see here, I had, that epsilon had 2 components to it. All right, let's try to notice better. Actually, I shouldn't erase that drawing. Okay, so I had a B sub L minus B sub C coming up like this. And I had a V sub R going like this. Where these meet is epsilon. All right. So remind ourselves here. Okay, so to remind ourselves that this angle right here. So remember, this angle was omega t minus phi, because this is the one that was lined up with the current. This angle between epsilon and this was angle phi. All right, which means that that this, let's see, if that's angle phi, that's 90 minus, this is angle phi as well. And this is cap B sub R. Okay, so then what do we know? Well, we have this phi, and we want to relate the phi to the side legs. How do they relate? Again, this is a right angle. Epsilon naught is my hypotenuse. How do they relate? Well, the tangent of phi is the opposite over the adjacent, or V sub L minus V sub C over B sub R. I mean, I'm trying to express the phase angle. I can actually express the phase angle. I can actually find the phase constant by knowing these amplitudes. Okay. And so doing this, I say, well, I know what B sub L is I cap X sub L. I know what B sub C is, minus I cap X sub C. And I have IR. So my I's cancel out. So I can actually get the phase angle from the amplitudes. Yeah, we use Pythagorean theorem. So this becomes phi is the inverse tangent of cap X sub L minus cap X sub C divided by R. And again, it's going to be ohms, ohms, and ohms. So everything is going to cancel each other out as far as units are concerned. All right, so that's how I can find the phase angle. Now, we have another interesting way of looking at this this particular concept or this particular circuit, and that is looking at its power. So remember, there's circuits. This is again voltage, and there's voltage in the circuit and current. Well, you can always talk about power as well. There's a power in an alternating circuit as well. All right, so we understand this this concept now of the phase angle. I can get the phase angle again straight from the amplitudes. Let's take a look at power. I'm going to keep this drawing up. Need it one more time. So let's look at the power in an alternating circuit, or power in an AC circuit. Okay, so essentially, if I'm looking at steady state behavior, in general, energy will be stored in the electric field and in the electric field and capacitor. And energy will be stored in the magnetic field of an inductor. So over time, the average energy stored in the, again, we'll say an RLC circuit. The RLC particularly. I mean, it is an AC circuit, is what we're talking about. So over time, the average energy stored in the capacitor and inductor will be a constant. However, power or energy, or there will always be a power loss I squared R in the resistor. All right, and so what we end up having is a relationship between electromagnetic energy coming into the system from the power supply and being balanced out by thermal losses by the resistor. The inductor and the capacitor are really not going to participate in this. Overall, their average their energy is, they have stored energy each in the electric field in a capacitor, in the magnetic field in an inductor. Overall, they're going to be a constant. So overall, you're going to have a balance. So essentially, the electromagnetic energy coming from the battery, or sorry, the power supply, will be balanced by the thermal losses from the resistor. All right. So on average, so the energy, so the electromagnetic energy or electromagnetic power from the power supply, AC power supply, will be balanced by the thermal power loss at the resistor. Okay. So more formally, I would write this, that the power in the AC circuit or RLC circuit, is since there is this balance, I can just express it as a power loss at the resistor, since they're balanced anyway. So I can call this as I squared R. Whatever I is in the, again, this is the instantaneous current in the circuit, whatever it is, I square it, multiply it by the resistance. Well, what is it? Well, it's, in general, it's going to be the general form of the current is its amplitude times the sine of omega t minus phi squared R. Again, I turn that into the amplitude times the sine function with the phase squared R. And so if I do that, I find out that the power ends up looking like capital I squared R, and then a sine squared of omega t minus phi. Okay, so that is, that's the relationship of the power at any point in time in the circuit. But the thing about circuits is I with alternating current circuits, we always talk about RMS or average power or RMS current, RMS voltage, right? And so what I really want to do is look at overall the average power. All right, so if I were to, so let's kind of go with this formula now. If we find the average power well, the average, let's see, we want to find the average power. Now again, these are amplitudes; they're not going to change. So we want to find the average power for AC circuit. You know, we express AC circuits. We talked about this a couple of chapters ago. We express them in terms of an average power. So we want to find the average power. Over many cycles. Well, the average, you can do this with integral calculus or trigonometry. The average of sine squared over many cycles is 1/2. You can show this with integral calculus or trigonometry. So again, this can be showed with integral calculus or with trigonometry. Or trigonometric relations, or integral calculus. What that means then is that if I want to talk about the average power, all I really have to do is sub out the sine squared for 1/2. So it just becomes 1/2 I squared R. And again, these are amplitudes, 1/2 I squared R. Or I can think of it this way. This is I over the square root of 2 squared R, and I can take my half and divvy it up square root of 2 each, put that in there. And remember from a couple of chapters ago, this is the root mean square current. So this is the same as I RMS squared R. So again, I can see in this derivation how I can get from the average power, and I can understand that I can express this directly in terms of the RMS current. So again, my P average can be written this way. I can write that P average is I squared RMS squared times R. the power that I'm putting into the circuit, the AC circuit from the power supply, is being counterbalanced by the thermal losses at the resistor. I don't have to account for what's going on in the inductor or capacitor because on average, that's stored, they're going to have stored energy, and that stored energy is going to be a constant on average. Okay, so again, this is a repeat of, you know, a lot of what we said before a couple of chapters ago. So it's kind of put this in a parking lot. Let me say a little bit more about it. So I can write again that the average power is I squared I RMS squared times R. Now remind ourselves, RMS means root mean squared. I discuss, because the current is constantly alternating, I don't really have any idea what the current is right now. All I can really say is I have to describe it statistically. So how you describe this is essentially, if you imagine taking a whole bunch of measurements of the current at any given time. You got a I1, I2, I3, I4, I5, on and on and on and on. You take a whole bunch of measurements of the current and you add up their squares. So I add, I find, all right, I take a lot of measurements. Of the current. I take the mean of their squares. It means I add up all their squares and I take the mean. Now again, when I do that, I have a current squared. When I get done adding up all the squares of all these values and dividing it by how many values there are, it's kind of like, you know, you guys all take an exam. I add up all of your scores and divide by 24 to get their mean score. Well, if I add up all the currents, all their squares, and I divide by the number of currents, what I'm going to get is something that's amperes squared. I need to get back to amperes. So I need to take a square root. So IRMS, the root mean squared, or RMS current, is obtained by taking the square root of this mean. Okay, that's what it means. It's a statistical measurement. We first saw this back in we talked about kinetic theory of gases, because there's so many particles, you have to talk about statistics. All right. So again, we need to speak in language of RMS. And as I said, all the DC equations that we had before work just fine. You know, again, I can use all the DC equations that I had before as long as I use RMS. I mean, I've said this before too. So we can use all of the DC equations from before. in AC as long as we use IRMS, VRMS, and P average for I, V, and P from before. As long as we do that, we're okay. And now, as I used before, I stated that I had a relationship, the IRMS was I divided by the square root of 2. This I up here is the peak value. That's the largest the value gets. That's the largest current you could possibly expect. That means that I can find the peak by taking the square root of 2 and multiplying by IRMS. So for instance, square root of 2 times, well, and again, IRMS, or I can do the same thing with any of it, right? So let me just give me a moment here. So again, I could write IRMS, so I can write IRMS as I divided by the square root of 2, VRMS as V divided by the square root of 2. And as I said a moment ago, this value that's right here is the peak voltage or the peak current. That's the biggest voltage you could possibly expect. Or in this case, this is the peak current. So let's say I'm talking about getting voltage out of my wall. Well, I always tell you, well, I mean, if I want to find a peak voltage, how would I do? Well, I solve here. I have the square root of 2 times VRMS. Now, if I go and I tell you, oh, my wall, like pretty much every house and business in America, has an RMS voltage of 120 volts. So VRMS is always 120 volts, but that's a root mean squared value. That means that half the time it's above 120 and half the time it's below. What's the biggest value you could possibly expect? Well, you take that 120 volts and multiply it by the square root of 2. You get that peak voltage will be about 170 volts. So you could get 170 volts out of your wall. Right? That's your peak voltage. In the United States. Pretty much anywhere in North America. I believe Canada and Mexico are also on the 120 volt 120 volts AC. Okay, and then of course you can also extend this even further. You can say that I can also say that IRMS can also be written as epsilon RMS divided by Z, the impedance, or epsilon RMS divided by what? Well, the impedance is always going to be the same. It's going to be square root of R squared plus the square cap X sub L minus cap X sub C squared. Let me take the square root of that. All right, so any other formula you can possibly think of, you can think of here. I mean, this is Ohm's law in the most general sense with the impedance for an RLC circuit. And again, we know that VRMS is the peak voltage over the square root of 2, and IRMS is the peak current divided by the square root of 2. So again, you can use now again, we're always used to IRMS is epsilon RMS over R for resistive circuit. Well, now you use Z. Z takes the place of what we use as resistance. Now the entire circuit has an impedance. The RLC circuit altogether has a combined impedance given by Z. And it's also in volts. Now, we can actually express the power another way if we wish. Okay, and so again, I wrote the average power as IRMS squared over R. Well, let's remind ourselves that, as I just said a moment ago, that I can also write this as what? I can also write that IRMS is epsilon RMS divided by Z. So let me do the following. Let me borrow one of these IRMSs, and I'll write P average is, okay, so I'm going to take one of these IRMSs and express it this way. Epsilon RMS over Z. The other IRMS, I'll just keep the way it is now. And I still have this R out here. All I'm doing is just replacing one of these IRMSs with the epsilon RMS over Z. Now, let me rewrite this. So P average is now going to be, well, I'm going to put the Z underneath the R. So I'm going to write this as epsilon RMS I RMS, like a voltage times a current, times R divided by Z. Okay, R divided by Z. Let's go back to our drawing here. So Z is going to be in the direction of epsilon naught. Okay, so if I look at this and say, okay, well, if I were to imagine, again, this right here is this piece of R, this is my angle phi. This is an adjacent, and this is a hypotenuse. My Z is along here. So again, my Z is along this hypotenuse. So I could say that cosine theta is epsilon coming along here. Oh, I'm sorry, adjacent or hypotenuse. So IR, or say V sub R divided by epsilon. Let's do that way. So cat V sub R divided by epsilon. And then what do I know? Well, again, epsilon is going to be essentially equal to I times Z. So this is going to be I times R. And again, we're talking about amplitudes here. This is going to be I times what? I times Z. All right. And so if I get rid of these I's, I find out that, I'm sorry, it's not, that's phi. I find out that I can actually express cosine of phi. Cosine of phi is this ratio of R over Z. This ratio of the resistance to the impedance. So in this diagram, using this diagram, I can actually write the average power as epsilon RMS I RMS times the cosine of phi. This cosine of phi has a special name. It is called the power factor. All right, and so in general, I could write the power a couple different ways, as I said before. I'm perfectly okay with writing it as P average, again, average power is I RMS squared R. But I can also write it as P average is, the voltage times the current, like you normally would think of, epsilon RMS, I RMS, but now times the cosine of phi. And the cosine of phi, according to this diagram, is the ratio of the resistance over the impedance. This is cosine of phi is called the power factor. This is very important in designing RLC circuits. So one wants to design a circuit, an RLC circuit, that delivers as much power as possible. So we want to make cosine phi as large as possible. We want to make the power factor and that's the name of the game with RLC circuits. You want to make the power factor, and of course the power factor can be positive or negative. So it can be positive or negative. It's not the cosine squared, it's just the cosine. Keep that in mind. Okay, so again, it's a factor that can be both positive and negative because we're talking about the cosine. All right, and so the idea is, let's say for example, we find that a load is highly inductive. So we find that a load in an RLC circuit is highly inductive. I analyze the power factor, right? Well, it can be made less so all right, by adding more capacitance. All right, and that thus reduces the phase constant and increases the power factor. Remember, cosine 0 is 1. So you really want to get the phase near 0. So recall, cosine of 0 is 1. So if you can get that phase as close to 0 as you can, you're maximizing the power delivery. You're maximizing the power factor for the RLC circuit. Okay. That is the last topic. I'm just going to work a few problems out, and then we'll call it a done deal. So, all right. So again, RLC circuit. All right, so we're looking at OpenStax 23.92. Again, chapter 23 in OpenStax is a very big chapter. All right, an RL circuit consists of a 40.0 ohm resistor, and a 3.00 millihenry inductor. A, find the impedance Z at 60.0 hertz. And at 10.0 kilohertz. And then B, B says compare these values of Z. This is a very good problem here. With those found in example 23.12, and I'm not going to go through that example, it's kind of implemented here. With those found in example 23.12, in which there was also a capacitor. All right, so that'll be add a capacitor in there. Okay, so we have an RL circuit. That means it just has a resistor and an inductor on it. Consists of a 40.0 ohm resistor, that's R, and a 3.00 millihenry inductor, that's cap L. A, find the impedance Z at 60.0 hertz and at 10 kilohertz. And B, we're going to compare these values of Z with those found in example 23.12, and in that one we're throwing a capacitor in there. All right, so that's all that's going on. All right, so for real estate purposes, I'm going to erase the board. So remember these numbers. We're going to compare it with two different frequencies. And again, I showed you in an earlier problem that unlike resistance, again, resistance is the impedance for the resistor. The impedance for the capacitance was the capacitive reactance, and the impedance for the inductor, which is the inductive reactance, vary with frequency. So we'll see how this works. So again, part A says, I want to find the impedance. All right. So the impedance is always given as cap Z is the square root of R squared plus in parentheses cap X sub L minus cap X sub C, quantity squared, take the square root of that. Now we know for this RL circuit, the resistor is 40 ohms. The inductor is 3.00 millihenries, 10 to the negative 3 Henry. All right. Now, at this point, since there is no capacitor, then cap X sub C is 0. There is no capacitive reactance. That means that goes away, and my impedance becomes the square root of R squared plus cap X sub L squared. Or what is cap X sub L? Remind ourselves, the inductive reactance is omega L, or otherwise known as 2 pi FL. I'll throw that in there. This becomes the square root of R squared plus, now again, 2 pi FL squared, well, 2 squared is 4, pi squared F squared L squared, square root. Okay, now that is the impedance for this particular problem. Now we want to look at it at a couple different frequencies. All right, so let me rewrite this function up here and remind ourselves these numbers. I need a little bit more space. All right, now the impedance. Squared R squared plus 4 pi squared F squared L squared. All right, so we're going to pick two different frequencies. So we're going to pick a frequency of, a lower frequency of 60 hertz. Let's see, of 60 hertz that would generally come out of your wall. Okay, and there we find out that the impedance will be the square root of 40 ohms squared plus 4 pi squared 60 hertz squared, and then the inductance is 3.00 times 10 to the negative 3 Henry. All right, we find out when we do this that the impedance at 60 hertz will be just 40 ohms. All right, so what that basically says is that at low frequencies, the impedance is negligible. Because look, the resistor is 40 ohms. That means that this term over here is almost negligible. And you get that because of this 3 millihenries. All right, so again, the impedance dominates at large frequencies. Why is that? Because remember, the capacitive reactance dominates the high frequencies because it literally is proportional to frequency. So small frequencies, the inductive reactance does not have a very large effect. It turns out that the capacitive reactance, it has a very large effect at small frequencies. At large frequencies, the inductive reactance is what dominates, but then the capacitive reactance becomes recessive. So one is strong and the other one's weak, right? Turns out that the inductive reactance for this small frequency of just 60 hertz is for this particular inductor is very weak, it's negligible. What about if the frequency is bigger, much bigger? We pick 10 kilohertz. So 10 times 10 to the 3 hertz, and we do the same problem again. We find out now that the impedance becomes, again, the resistor is 40 ohms, that doesn't change, plus 4 pi squared. Now we stick the big frequency in, 10 times 10 to the 3rd hertz squared, that's squared, times, again, the inductance, 3.00 times 10 to the negative 3 Henry. Square root of all of that. When you do that, you find out that now, you know, the impedance is going to be much bigger than the resistance. It's 192.7 ohms. All that says is that the inductance, the inductive reactance, is dominant at high frequencies. It's weak at low frequencies. All right. So let's remember these values, and then we'll do part B, and we'll see how the capacitor comes into play and affects these numbers quite a bit. All right. So we're going to take the capacitor at a low frequency, and then we're going to take the capacitor at a high frequency, and we'll see how it plays. All right. So let's put part A's answer in the parking lot. So a reminder ourselves that if F equals 60 hertz, the impedance is 40 ohms, and if F equals 10 kilohertz, the impedance became 192.7 ohms. All right, we'll now stick a capacitor on here. All right, so the same inductor and resistor are now going to be connected with a 5.00 microfarad capacitor. All right, so I'm going to erase this work here. So now the capacitive term, the capacitive reactance will wake up, because now we're going to stick a capacitor on it. All right, and so for part A, what did we have? Part A, we had a time-varying power source, and we just had a resistor and an inductor. Right? That's what we had before. Now we're going to use the same resistor and inductor, but now we're going to add a capacitor. Now we're going to have an RLC circuit. And our capacitor, so remember, our resistor was 40 ohms. Our inductor was 3.00 millihenries, or times 10 to the negative 3 henries. And now our capacitor, we're gonna stick a 5.00 microfarad capacitor on there. Let's see what happens. All right, so we're gonna go back to those impedance formulas, but this time we have to wake up the capacitor reactance. So the full-blown impedance formula now, again, in general, it's Z is the square root of R squared plus cap sub L minus cap sub C squared, square root. And again, Z, let's kind of work this out here. So Z will be, again, square root of R squared, again, cap sub L is 2 pi FL, and cap x of C is minus 1 over 2 pi FC. That is squared. We take the square root of all of that. All right, that's the general full-blown impedance relationship. All right, and so this term wakes up. All right, well, let's look at Let's look at 60 hertz. All right, so now we're gonna, if I can put this all on the board. C is gonna be, 40 ohms, that's a resistor, squared, plus, all right, here we go. Make this bracket now. 2 pi 60 hertz. The inductance, 3.00, 10 to the negative 3 henries, minus 1 over 2 pi 60 hertz, 5 microfarads. Hang on. Not enough space. Let's do that. We're going to try this again. It's a long chain of numbers. All right. So again, we're doing 60 hertz. All right. All the way to the left. C, 40 ohms squared plus, we have brackets, 2 pi 60 hertz times 3.0 times 10 to the negative 3 henries minus 1 over 2 pi 60 hertz times 5 times 10 to the negative 6 farads. Okay, this gets squared, and this all gets under a square root. All right, when you work all of that out, again, this term here is for the, you can barely see this, can't you? Let's see, find myself here. Try to write this so you can see it in the parking lot. It kind of goes off the board here. All right, so again, I have F equals 60 hertz and F equals 10 kilohertz. For the RL circuit, and I want the RL circuit. These are the Z values, and this is for the RLC circuit. Okay, so before, remember what I had before my numbers? I had 40 ohms and 192.7 ohms. If I calculate this big mess right here, I'm actually going to find out that I'll have 531 ohms. So my Z will equal, for this particular calculation, 531 ohms, when before, at the same frequency, it was only 40 ohms. At the same frequency, the 60 hertz, the inductor pretty much had no effect whatsoever. The inductive reactance had no effect. It was negligible. But remember, the capacitive reactance is dominant at low frequencies. The capacitive reactance had a large effect. You square it, and you notice that instead of having 40 ohms, which is basically the resistance of the resistor before, now it's been jacked up to 531 ohms. So you can see the dominant effect of the capacitor at low frequencies. What about the high frequencies? All right, so if we go to high frequencies, let's see what I can do here. At high frequencies, we're talking about 10 kilohertz. What happens? All right, so yeah, rewrite this. So it's the same calculation, except I'm going to stick the frequency of 10 kilohertz in here. Let's see if I can try to be smart about this. All right, so 10 times 10 to the third hertz. Same inductor, 3.0 times 10 to the negative 3 henries. And let's see, over here, minus 1 over 2 pi. Again, I have 10 times 10 to the third hertz times 5 times 10 to the negative 6 farads. Okay, again, this bracket is squared, and that's square roots. Comes all the way across. So if I do that entire calculation, I find out that now that my impedance is 190 ohms. So now 190 ohms. Well, that's not much different at all from what we got from the RL circuit. So at this point, what that says is that the RL circuit at high frequencies is very much dominated by the inductor, but the capacitor, the contribution from the capacitor is negligible. So again, as you can see from these calculations, at low frequencies, the inductor dominates, the capacitor is, I'm sorry, at low frequencies, let me say that again, at low frequencies, the inductor has a weak contribution and the capacitor has a strong contribution. At high frequencies, the inductor has a strong contribution, the capacitor has a weak contribution. Okay, so again, let's kind of summarize. We're kind of writing this out, remind ourselves. All right, so again, this is a proof. This was actually part B. All right, part B. All right, so what did I just show you from this problem? What's the takeaway from this problem? So again, problems are all supposed to teach you something, right? So 23.92 should have a takeaway. What should you walk away understanding at this point? Well, again, remember the impedance. Square root of R squared plus capex of L minus capex of C quantity squared. And again, Z is R squared plus, we have bracket square of 2 pi FL minus 1 over 2 pi FC. At low frequency. Right? The capacitor dominates. And the inductor is weak. At high frequencies, F. The inductor dominates. And the capacitors. And you can see it from the formula. It's no surprise. Why? Because the inductive reactance, okay, that's the biggest effect on the impedance. The inductive reactance is directly proportional to the frequency. So small frequency, small inductive reactance. High frequency, large inductive reactance. The capacitive reactance is inversely proportional to frequency. Small frequency, large capacitive reactance. Large frequency, small capacitive reactance. So again, there's a difference in the functional relationship or the functional dependence of the frequency on both the inductive reactance and the capacitive reactance. That's why they behave the way they do. All right. Work another problem. Open stack's 23.96. That says to receive AM radio. You want an RLC circuit. I mean, this is one of the things that got me into physics. I used to have little radios back in the 1970s when I was a kid, and I take that thing apart all the time. I'd look at the resistors, the capacitors, the inductors, and I thought that was like the neatest thing in the world, that this somehow played music, right? And it's just a bunch of circuitry. I mean, to me, that was just amazing to me. So to receive an AM radio, you want an RLC circuit that can be made to resonate. Between 500 and 1650 AM band kilohertz. Anybody listen to AM radio? That's the band for AM radio, the official band. All right, this is accomplished with a fixed 1.00 microhenry inductor. Connected to a variable capacitor. What range of capacitance is needed? All right, so again, to receive AM radio, you want an RLC circuit that can be made to resonate between 500 and 1650 kilohertz, the AM band. This is accomplished with a fixed 1.00 microhenry inductor connected to a variable capacitor. What range of capacitance is needed? All right, so this is where we're going to talk about resonance again. So I derived the resonance frequencies, so we're going to talk about that now. So remember, we're in the AM band, and we have 1 microhenry inductor. That's in the radio. We're going to have it connected in series with a variable capacitor. So remind ourselves now, the resonances occur for omega naught equals to 1 divided by the square root of LC. Really beautiful, simple formula that says that my circuit resonates. I can change the values of the angular frequency which my circuit resonates by just changing the inductance and the capacitance. So this is the resonant frequency for RLC circuit, remind you. All right, so I know that omega is 2 pi f, so omega naught would be 2 pi f naught. So I can actually write this as f naught is 1 over 2 pi square root LC. All right, and so I'm going to be, L is a constant, right? And so I'm going to have a minimum frequency and a maximum frequency for the AM radio band. So my F min would occur at C max. So 2 pi square root of L C max. Or actually, we want to solve for C. Let's solve for C first, and we'll talk about maximum. All right. So let's just we want to talk about the variation of the capacitance. Let's solve for the capacitance. So let's change partners here. I have the square root of LC, a little algebra, is 1 over 2 pi F naught. All right, and I'm going to square both sides. I have LC is 1 over 4 pi squared F naught squared, and of course I'll divide simply by L. So I have C is 1 over 4 pi squared F naught squared L. So that means if I have to vary my capacitance such that, granted the radio station is going to have a minimum frequency and a maximum frequency in this band. I need to be able to tune to any of those frequencies. So if I look at the minimum frequency, F min, that will occur, again, this will minimize my denominator, which maximizes my fraction. That means that'll occur when the capacitance is max. So I would say that C max would be 1 over 4 pi squared F min squared L. So my C max would have to occur when I'm at the minimum frequency, the 500 kilohertz. Remember, the AM radio band goes from 500 to 1650. So my minimum is at 500. So 4 pi squared, 500 times 10 to the 3 hertz. And my inductance is 1.00 times 10 to the negative 6 Henry. C max will be 1.01 times 10 to the negative 7 farads, which is 101 nanofarads. That's the maximum. All right, so I'll write that in a little parking lot here. C max occurs at F min, 101 nanofarads. Great. Well, how about the, okay, so the maximum value of the capacitance would be 101 nanofarads. Well, the minimum value would have to occur when I maximize the frequency. All right, and so I can kind of do the same work, put the max in there for min, and then basically the same work, except now instead of 500, I'll put 1650 in here so I can fit that in there. So again, I know you can't do this, but once in a while you have an advantage having a whiteboard. There you go, 1650 kilohertz. When I do that, I find out that I have 9.30 times 10 to the negative 9 farads. Which is 9.30 nanofarads. So my C min is 9.30 nanofarads. So my resistor, my capacitance has to be able to be bounded by these two values. I need to be able to change the capacitance, the variable capacitor between 9.30 nanofarads to 101 nanofarads in order to be able to tune any station in the AM band. All right. One more problem, and that's it for this lecture. So one more problem. So OpenStax 23.105. It's not often you see problems that are in the 3-digit numbers. That's how big that chapter was in OpenStax. All right, OpenStax 23.105. Last problem. Okay, an RLC series circuit has a 200 ohm resistor. And a 25.0 millihenry inductor. At 8,000 hertz. The phase angle is 45 degrees. That's our feet, remember. 45.0 degrees. All right. A, what is the impedance? B, find the circuit's capacitance. C, if VRMS equals 408 volts, and cap VRMS is the amplitude, 408 volts, so this would not be in the United States, this would have to be somewhere in Europe probably, is applied. What is the average power supply? So this is a nice problem that sums up the last stuff we studied. All right, so here we go. An RLC series circuit has a 200 ohm resistor, that's R, and a 25.0 millihenry inductor, that's cap L. At 8,000 hertz, that's F. The phase angle is 45 degrees, that's phi. A, what is the impedance? Okay, that's capital Z. Find the circuit's capacitance, okay, that's C in the RLC circuit. And then if VRMS is 408 volts, I put into a power supply that has a voltage amplitude of 408 volts. What is the average power supply? All right, so here we go. So it's going to go over a lot of good stuff here. So remember these numbers, a lot of numbers. All right, part A. So let's look at what we know. All right, so again, looking at part A, what do we know? We know the resistance. We know we have a resistor is 200 ohms. We know that. We also know the inductance. We have an inductor on it. And that inductor has an inductance of 25.0 times 10 to the negative 3 henries. We also know the frequency which we're operating. The AC frequency is 8,000 hertz. And we have the phase angle. The phase angle is 45 degrees. All right, so they want us to find Z. And we can kind of do it in a really clever way, is reminding ourselves how Z relates in the phase angle. Remember the phase angle. I can write from that geometry I drew earlier, I can write that cosine of B from that geometry is equal to R over Z. I know R, I don't know Z, but I can get it from this phase angle. That's very nice and easy. So I can actually switch partners here and say that Z is R over cosine phi. Usually, impedance is a fairly complicated calculation, but I mean, I got with the phase angle, the power. I mean, or if you know the power factor, you can get it quite easily. So that's another nice thing about the knowing the power factor. So let's see here. Again, so, we want the resistance is 200 ohms divided by the cosine of 45 degrees. We have that the impedance is going to be 283 ohms. Great, that's part A. Put that in the parking lot. That's another important thing to know. So again, the impedance is another variable, you know, 283 ohms. Great. Part B says find the circuit's capacitance. Okay, now we have to actually tease out what the impedance is, and we have to do some relatively ugly algebra to find the capacitance. Capacitance is buried in there. All right, so let's do that. We know the impedance. What we don't know now is the capacitance. So we know the frequency. So remind ourselves what everything looks like in grand glorious form. And I'm on part B now. The impedance is the square root of R squared plus, let's just kind of write the whole thing out. Well, we know it's cap X of L minus cap X of C quantity squared square root. Right? And so let's see here. We have, let's kind of write things compact before we start getting out the capacitance. So let's just, let me flip about the equal sign. So I have, again, the square root of R squared plus, I have cap X of L minus cap X of C, quantity squared, square root, equals Z. I'm going to square both sides. I have R squared plus cap X of L minus cap X of C equals Z squared. Again, this is squared. What am I after? I'm after something that's inside of that term, the cap X of C term. So what I'm going to do, I'm going to put R squared on the other side. So I have cap X of L minus cap X of C squared is Z squared minus R squared. And now I'll take the square root of both sides. Cap X of L minus cap X of C is plus or minus, remember, square root of Z squared minus R squared. Now the question is, well, which is it? Is it plus or is it minus? That's where we have to kind of write out what these are. So I don't know what they are yet, right? So we write this as what? This is cap X of L is 2 pi f L. Cap X of C is minus 1 over 2 pi f C. And then that's going to equal, and if you look at it, well, we have a fairly large frequency. And so we see that 2 pi FL is going to be a big positive number minus 1 over 2 pi FL is going to be a little number, right? Because the denominator is going to be huge. So we see that because this is a high frequency, the inductance is going to dominate. And so this is going to be a positive value. So we pick the positive roots. Why? Because the inductance dominates. You know, positive roots because inductance dominates at high frequency. Okay, so we got down to here, so I'm going to have to, you have to remember what we did down here. So I mean, I don't have enough space. So I'm going to take this equation and move it up to the top, and let's finish the problem. And so I'm going to erase these lines of algebra. So sorry about that. All right, so we've gotten to this line. I'm just going to rewrite it to the top. All right, so what do we know? Again, we have 2 pi FL minus 1 over 2 pi FC is now going to be the square root of z squared minus r squared. Great, so more algebra to go. So now I'm going to throw the inductance term on the other side. So I'm going to throw the inductance term on the other side and multiply through by negative sign, right? Because I throw the inductance term on the other side, it becomes negative, but then I'm left with a negative capacitor term. So I'll just multiply. I'll do 2 steps of algebra in 1. So what I get here now is 1 over 2 pi FC is 2 pi FL minus the square root of z squared minus r squared. All right, and then what I'm going to do at this point is I'm just going to flip everything upside down. So I'm going to flip my equation upside down. So the left side goes upside down, the right side goes upside down. Everybody inverts, right? So now I have 2 pi FC is 1 over all this stuff, 2 pi FL minus the square root of z squared minus r squared. And then I want to get c by itself. I'm going to divide everything through by 2 pi f. So finally I have c, the capacitance, 1 over a whole bunch of stuff, 2 pi f brackets. We have multiplied by 2 pi FL minus the square root of z squared minus r squared. Now all I got to do is put some numbers in or work this out. Okay, so hopefully I have enough whiteboard for that. All right, here we go. C. As far left as I can go. C is equal to, am I on the whiteboard? Yes, I am. Good. All right, so it's 1 over all this stuff. So I'll put a 1 somewhere in the middle here. Put a big fraction bar, like that. And then start filling stuff in. All right, 2 pi, 8,000 hertz, bracket, 2 pi, 8,000 hertz. The inductor, 25 millihenries. All right, minus, all right, so we figured out the impedance before for the power angle. So 200, so we have squared, we have 283 ohms squared minus the original resistor, 200 ohms. And don't forget to take the square root of all that stuff. There you go. So you work all that out, you find out that the capacitance, you work this all out, and I'm just going to have to erase this top line here to write the answer. Put all this in your calculator, you find out that the capacitance you will see, and you will calculate, is 1.88 times 10 to the negative 8 farads, which is 18.8 nanofarads. That is the capacitance of this RLC circuit. Now we know RL and C, the frequency, the power angle, the impedance. We know about almost everything we could possibly know. At this point, we're going to do a power calculation real quick. And so we'll just kind of keep that up there. For part C says, okay, let me reread this. Part C, remember, says if capital VRMS is 408 volts, that's coming out of your wall, is applied, what's the average power supply? All right. So again, let's do that. Part C. So part C says, well, what we're going to use, we're going to say, well, P average is IRMS VRMS. Right? Again, I can use all of the DC equations as long as I use RMS variables. I know one other thing, and that is that IRMS is VRMS divided by Z. Remember, in the RLC circuit, remember in a basic resistive circuit, the impedance is just the resistance. In an RLC circuit, the impedance is the impedance. I mean, it is a full-blown impedance that has the capacitive and inductive reactance intertwined. So I combine these two, and I find out that the average power is VRMS squared divided by Z. And so I was told what VRMS squared is. I mean, I was told that's coming out of the wall. I mean, I can stick this in my laundry list of stuff as well, I guess. 408 volts, right? So it's either, some military thing, or you're in another country, because you're not going to plug into a wall and get 408 volts in the United States, Mexico, or Canada, that's for sure. So 408 volts, you might get 240 out of your garage, squared, and divided by the impedance of 208 ohms, like we had before. 200, I'm sorry, what am I getting that? 283 ohms. All right, all together, you'll find out that the average power supplied to your circuit is 588 watts. All right, that is all I have for chapter 23.